All right, chemistry, this is your video lecture for Chapter 7, Section 4. We're going to be determining chemical formulas. So, at the end of this video lecture, I want you to be able to define empirical formula, there's a new one for you, and explain how the term applies to ionic and molecular compounds. Hopefully at this point, you're recognizing the significance of that term ionic compound and molecular compound, one referring to alternating negative and positive ions in a crystal lattice, whereas one, molecular, refers to covalently bonded nonmetals. Then determine an empirical formula from either percent or mass composition data. Then explain the relationship between the empirical formula and the molecular formula of a given compound, right? Explain the relationship. Then lastly, determine a molecular formula from an empirical formula. So actually calculate. So here we go. So here's a graphical representation of empirical formulas and actual formulas. If we know that the empirical formula for ammonium nitrite is NH4NO2, this is the actual formula, we can reduce certain subscripts to make a simple representation. So we have 2 nitrogens, 4 hydrogens, and then 2 oxygens. These can all be divided by 2 to result in 1 to 1. It's a 1 to 2 to 1 ratio. So the empirical formula in its simplest sense is the actual formula reduced as far as it can go. Now that's not super useful in a lot of ways, except for taking measurements from an unknown sample, and I'll show you how that works. But for now, know that an empirical formula consists of the symbols for the elements combined in a compound with subscripts showing the smallest whole number ratio of the different elements in that compound. I'll say it again. Smallest whole number ratio. Smallest whole number ratio. For an ionic compound, the formula unit is usually the compound's empirical formula, because it's going to be as reduced as it can be to give the simplest ratio of charges. For a molecular compound, however, the empirical formula does not necessarily indicate the actual number of atoms present in each molecule. For example, the empirical formula of the gas diborane is BH3, but the molecular formula is B2H6. That might make more sense because we just said diborane. We'd think, well, there should be 2 borons there, right? Why is there only 1 in BH3? Oh, because that's the empirical formula. The actual molecular formula is B2. Okay, that makes sense for diborane. Notice what all we've done to get to the empirical formula is divide both of those by 2. To determine a compound's empirical formula from its percentage composition, which is something we learned how to do last section, we begin by converting percentage composition into mass composition, which might seem very, very complicated, but it's probably the easiest thing you're going to do this year. Assume that you have a 100-gram sample, and that's it. You go from assuming there's 100 grams in the sample, because remember, the mass percent does not change based on the size of the sample. So, for example, the percent composition for diborane is 78.1% boron and 21.9% hydrogen. Now, you can already do this, so I'm not going to explain that again. You can do that last section. So, if we assume the 100-gram sample, the 100-gram sample of diborane would contain 78.1 grams of boron and 21.9 grams of hydrogen, right? Because 78.1% of 100 is 78.1. That is why we want to assume a 100-gram sample. It makes things a lot simpler for us as we move forward. Next, the mass composition of each element is converted into a composition in moles by dividing by the appropriate molar mass. And you can already do this. We can convert grams of an element into moles of an element using the molar mass found on the periodic table. So make sure that you pay attention to what unit you're trying to convert out of and what unit you're trying to convert into, and you'll make this a breeze. So 78.1 grams of boron is actually 7.22 moles of boron, And 21.9 grams of hydrogen is actually 21.7 moles of hydrogen. These values give a mole ratio. The ratio of boron to hydrogen in terms of moles is 7.22 to 21.7. But we have to find the smallest whole number ratio because that is what an empirical formula is. It's the smallest whole number ratio. Remember, I repeated myself several times earlier in the video. In order to do that, we're going to divide each number of moles by the smallest number in that existing ratio. And we did that last video, didn't we? 7.22 is smaller than 21.7 because we know numbers. And so we see that 7.22 divided by itself is just 1. So it's 1 mole of boron for every 3.01 moles of hydrogen, which is 21.7 divided by 7.22. Because of rounding or experimental error, a compound's mole ratio sometimes consists of numbers close to whole numbers instead of exact whole numbers. In this case, the differences of whole numbers may be ignored and the nearest whole number can be taken. So 3.01, we're just going to assume that's actually 3. So the ratio is 1 to 3, which is what we already know the formula to be because it's B2H6 for the molecular formula and BH3 for the empirical formula. So quantitative analysis shows that a compound contains, and this is a new one, right? This is a new compound, new sample problem, 32.38% sodium, 22.65% sulfur, and 44.99% oxygen. Find the empirical formula for this compound. So we know the percentages of each of the elements in the compound. We're trying to find the empirical formula, which is the smallest whole number ratio of elements. So what are we going to have to do? We're going to have to go from the percent composition into the mass composition. Remember, we're going to do that by assuming a 100-gram sample. Once we have the mass, we can convert the masses of each of those 3 elements into the moles of each of those 3 elements, and then we'll be able to get to the smallest whole number mole ratio of atoms. So here we go. See what it looks like. Got 3 elements. I've already assumed the 100-gram sample, so I got 32.38 grams of sodium, 22.65 grams of sulfur, and 44.99 grams of oxygen. I'm going to look at the periodic table to get the molar masses for each of those, and I'm going to be sure to place the grams on the denominator and the moles on the numerator so that I can cancel out of grams and into moles. Some simple calculations let me know that I have 1.408 moles of sodium, 0.7063 moles of sulfur, and 2.812 moles of oxygen. I need to find the smallest whole number ratio of these atoms, however. And so the compound contains atoms in the ratio of, and these are the numbers that I just generated on the previous slide, 1.408 moles of sodium to 0.7063 moles of sulfur to 2.812 moles of oxygen. So what do? We divide by the smallest number present, which in this case is the 0.7063 from the moles of sulfur. Divide all 3 numbers by the smallest value present, and we come out with a 1.993 moles of sodium to 1 mole of sulfur to 3.981 moles of oxygen. Because those are so close to the whole number, just the tiniest bit of rounding yields a mole ratio of 2 to 1 to 4. That leaves us with an empirical formula of Na2SO4. Now, the empirical formula contains the smallest possible whole numbers that describe the atomic ratio, right? The ratio of elements, the smallest whole number ratio possible. But the molecular formula is the actual formula of the molecular compound, as you would actually see it in nature. The molecular formula may or may not be a correct molecular formula. Sometimes it is, but sometimes it's not. The relationship, because remember, we have to explain the relationship between empirical formula and molecular formula. That was your 3rd objective for this video. Can be written as follows. A multiplier, some multiplier, which we don't know right now, so we'll represent it by a variable, x, multiplied by the empirical formula equals the molecular formula. The formula masses have a very similar relationship. Again, there's some multiplier. We don't know what it is right now because it's going to be different in every circumstance. Multiplied by the empirical formula mass, right? Not talking about molar mass right here. Formula mass of an individual compound equals the molecular formula mass. To determine the molecular formula of a compound, you must know the compound's formula mass. Dividing the experimental formula mass, dividing that mass by the empirical formula mass gives you that unknown X, right? It gives you that multiplier. So a compound's molecular formula is numerically equal to its molar mass. So the compound's molecular formula can also be found given the compound's empirical formula and its molar mass. So, for example, we have 3 different substances here who all share the same empirical formula. CH2O, formaldehyde, acetic acid, and glucose all have a smallest whole number ratio of elements as CH2O. But the molecular formulas are very, very different. Formaldehyde, the molecular formula is the same as the empirical formula. It's CH2O. But acetic acid is actually C2H4O2. We have to multiply that ratio by 2. N is equal to 2, or that unknown multiplier, which in the previous slide I represented as X. We have to multiply everything by 2. And then glucose, my multiplier is 6 because the actual formula, the molecular formula, is C6H12O6. And so that X, that multiplier, is 6. Now, because there are so many more atoms in each of these progressive molecules, we see that the molar masses of the molecular formula are very, very different, right? 30.03, 60.06, and 180.18. But notice that they all can be found by multiplying the mass of the empirical formula, which would be 30.03, by 1, right? That'd be your multiplier if you're talking about formaldehyde. Or if you're talking about acetic acid, your multiplier would be 2, and the molar mass would bump up to 60.06. Or if you're talking about glucose, your multiplier would be 6, and your molar mass would bump up to 180.18.
The empirical formula of a compound is the simplest formula for that compound. The molecular formula, on the other hand, shows you exactly how many of each type of atom is in the molecule. The molecular formula is always a multiple of the empirical formula. In some cases, 2 compounds can have the same empirical formula but different molecular formulas. For example, formaldehyde and glucose have the empirical formula CH2O. But glucose has 6 times as many carbons, hydrogens, and oxygens as formaldehyde. In this case, more does not mean more of the same. Formaldehyde is used in preserving specimens and embalming bodies. Glucose, on the other hand, is a type of sugar.
All right, let's get on to some sample problems because this is what you're doing. This is what you're doing for the whole section. You're doing calculations. So, in sample problem M, that's the previous sample problem we did in this chapter, the empirical formula of a compound of phosphorus and oxygen was found to be P2O5. Experimentation shows that the molar mass of this compound is 283.89 grams per mole. What is the compound's molecular formula? So let's slow down and make sure we know what's being given by the problem and what we have to supply. The empirical formula is P2O5. The problem is giving us the empirical formula. It's P2O5. Experimentation, meaning you don't have to go get that number. The problem has to give you that number. The molar mass of the compound, the actual compound's formula, is 283.89 grams per mole. And now we have to find the molecular formula. So we've been given the empirical formula. We need to find the molecular formula. And so remember this relationship. We have a multiplier multiplied by the empirical formula is going to equal the molecular formula. So in order to find out what that multiplier is, we rearrange this equation algebraically. Goodness gracious. Rearranging algebraically. I hope we can handle this. Divide both sides by empirical formula. It'll cancel out from the left side and be left as the divider for molecular formula. So the molecular formula mass is numerically equal to the molar mass. So we know that the molar mass is 283.89 grams per mole. So the formula mass is 283.89 AMU. Getting on to the empirical formula mass, right? We need to calculate that. We can calculate that very, very easily because the problem told us that the empirical formula was P2O5. The mass of the mass of one phosphorus atom is 30.97 AMU. The mass of an oxygen atom is 16.00 AMU. And so multiplying the mass of phosphorus by 2 and the mass of oxygen by 5, we get the empirical formula mass of 141.98. Now, I'm already seeing the relationship between 141.94 and 283.89, but I won't ruin the surprise. Oh yeah, I will. I see that when I divide both of those numbers out, they're simply separated by 2. So x, that multiplier, is 2. So I take that empirical formula that I started with at the very beginning of the problem, P2O5, and I multiply all of its subscripts by 2, the value of x. And so the molecular formula here is P4O10. All right, chemistry, I'll give you one warning. This is not stuff that you memorize simply by reading. This is stuff that gets beat into you through repetition. So use the sample problems in your textbook. Use the preparation problems that you have. Use the videos online to aid in those. And then when it's time, when you guys get your worksheet, make sure you are using your notes to make sure that you are following the proper system. All right, chemistry, I will see you next period.